Through this course, we first saw fully deterministic approaches in which all the quantities, including observations and unknowns, were treated as deterministic quantities, and these can be solved by minimum norm, least squares, minimum norm, least squares, or direct inversion methods, depending on the properties of linear operator. And we can also add weight norm or regularization to our solution. In contrast, in stochastic methods, we have some statistical information about our unknowns, and we treat our observations as random quantities under static, and they can be divided into two categories. In the first category, we treat our unknown as a deterministic quantity. We can use maximum likelihood estimation under static. And in the second class of stochastic methods, we also treat unknown as a random quantity, and these methods are called Bayesian estimation methods. So we have some prior information about our unknown, and we estimate using that. And um, one kind of Bayesian approach is MMSE estimation, minimum mean square error estimation. We require some Monte Carlo methods for numerical integration in this method, but in specific case LMMSE, for example, we can also find the solution using autocorrelation matrices more easily. But minimum mean square error method requires computational expensive task, and it only makes sense when the experiment is conducted many times. And this is one possible choice of error function. So it may not make sense in some contexts. Another Bayesian estimation method, map estimation, where you find x that maximizes the posteriori distribution given the observation. Not that in stochastic framework, regularization and weight norm solution were just guesses, educated guess. I'm deterministic approach. You must guess the correct regularization or weight norm for the problem, but in stochastic methods, we just find them from the statistical information like autocorrelation matrices of noise or unknowns. So it's more beneficial in this sense. Also, in stochastic methods, the solution doesn't depend on properties of a linear operator matrix representation. So, for example, in LMMSE case, there always exists a solution. Doesn't depend on y. Solution can depend on autocorrelation matrices, but in this setting, in this case, it doesn't depend. So we have similar optimization problem in both deterministic and stochastic methods, and we may not have an analytical closed form solution. We should use numerical optimization in such a case. Also, we can use numerical optimization to find the solution in an efficient way. And there may be a closed form solution which requires computational expensive tasks or occupies the meshes can occupy a lot of space in memory, and we can use numerical optimization for feasible solution.